Yeah, thank you very much. Thank you for the opportunity to speak here today. So this is about the dress splitting in equivariant homotopy theory. So let's just recall some notation and then get the dress splitting on the board, and then I will tell you what this is about. So, okay, so we've already seen this once or twice in the last couple days, that we have a map, let's call it phi, from the Burnside ring of a finite group G to a product of copies of the integers, where H runs over conjugacy classes of subgroups of G. And we've seen that this is an injective ring homomorphism. It's often called the homomorphism of Marx. And maybe let's recall what it does. So it sends a G set X to the cardinalities of the fixed point sets for all H. So we've seen that before. I think what we didn't really talk about is that the same story is still true if we invert elements in the integers. So it's also true for the p-local Burnside ring. And I will also denote the map by phi. So again, we have an injective ring homomorphism, and here we get copies of the integers with all primes but p inverted. Okay. I need one more definition. Group theoretic definition. So let's say a group G is called P perfect for some prime P. If the following holds, if G has no normal subgroup of index the power of P. Yeah. Should I write proper? I guess it should be clear. It shouldn't be one, sure. Okay. And now there's a classical theorem by Dress, which says the following. It says if you care about idempotent elements, in the p-local Burnside ring, and I guess I should say primitive idempotence here. So idempotence that we cannot write as a sum of other idempotence. Then this is in bijection with conjugacy classes L of p-perfect subgroups of G. So there's a classification of idempotent elements in the p-local Burnside ring of a finite group. It's a bit more complicated for compact Lie groups, but we can do something about it. And what does it do? So if we have a p-perfect subgroup L, or its conjugacy class, we get an idempotent element EL. So let me describe what this looks like. Oh, I shouldn't do this. So we can use the map phi to describe what EL looks like. We'll completely determine EL. And since we're mapping to Z, and we have an idempotent element, we can only take values 1 or 0. So we only have to know when it's 1, when it's 0. And this is a bit complicated in group theoretic, but I think I want to say that L is subconjugate to H, and L is minimal in H with the property that it's normal, and H mod L is a P group. So this looks a bit complicated and we don't really need it later, but yeah. Oh, this is subconjugate. I guess some people would write something like this. I mean, up to conjugation, L sits in H. So here I should probably write L prime, because only conjugate of L will actually sit in H as a normal subgroup. No, I don't think so. I can check my notes, but I think it's correct. It's right. I guess if you like group theory, there is this construction that if you have a group, you can form OPH, and I require that this is G conjugate to L. But you can ignore this if you're not a group theorist. So this is this case. Upper P, okay. I'm not a group theorist. All right. So this will give us what I like to call address splitting. So what does it say? Okay, so we know the idempotent elements in AGP, and this will give us a splitting of rings. So AGP as a ring is the same as a product of submodules generated by EL, where this runs through the idempotents. So L runs over all the p-perfect subgroups. So a priori, this is only a module, but since EL is idempotent, this is actually a ring with unit EL. And we can also write it in a different way, where we write it as AGP, and then we invert the element EL, the idempotent. Then you also see that EL, since it's idempotent, is a unit in that ring, or is the unit element in that ring. Okay. So what's the next step? I guess I should observe here that this is actually true as Mackey functors. So we've already seen that the Burnside ring has transfers and restriction maps, and that they behave in a nice way. So here it's actually true that a blank, where you plug in subgroup, is the same as a product over all the. So now we're in trouble because EL really lives in here, so we have to restrict first to our subgroup before this makes sense. So restrict to the subgroup you plug in, and then look at the submodule of A of your subgroup. This is true as Mackey functors is compatible with restriction and transfer. So this is the address splitting. And in the first maybe 15 minutes, I'd like to say a little bit about how it relates to what Jesper will talk about, the uncompleted Siegel conjecture. And then in the rest of the talk about my PhD project, talk about equivariant stable homotopy theory and the stable address splitting. So this is the rough idea for today. Sooner. Yeah. It's always the same, always the p-perfect subgroups. So here I'm actually just rewriting the factors. Okay, so this will be part 1 of my talk. Let's call it relation to Jesper's work. Jesper should be here today, but he has to go to a meeting in Stockholm, so I guess he's on a plane right now. Yeah, so the first thing I want to do is look at one of the factors here, kind of the canonical one or principal one that comes from the trivial subgroup, which will always be p-perfect. So consider the principal idempotent. E. I guess it's a bit of a silly notation because both is called E. Let's try to make sense of this complicated group theoretic description and see what it looks like in the case of EE. So if we look at the marks of EE, we'll sometimes get 1, sometimes get 0. And here it turns out that this is 1 if H is a P group, and 0 otherwise. So here it really simplifies a lot. And then it shouldn't be too hard to see that if we look at the submodule or subring given by EE in this idempotent splitting of the ring, then this can be identified with the Burnside ring of G, where I only allow finite G sets with isotropy a P group, so with P isotropy, and then localize away from P. And you can actually identify this object with some more rings. So let's have a lemma. So this thing here, the Bernstein ring with restricted isotropy, only p groups, can also be identified with the Bernstein ring of the p fusion system of G, and then p local. So let's prove this, because it doesn't take too long. Okay. So the left-hand side actually satisfies the hypothesis for the, I think it's called the fundamental theorem of green or something like that. Fundamental theorem of green rings. And it says that this value here can be computed by a limit where we only have to evaluate at p groups. So this runs over all p groups. It's an inverse limit. And then you see that this is the definition of f-stable elements, and it's the Bernstein ring of the fusion system. So this is the same as f-stable elements in a pseudo-subgroup, p local. And this by definition is the Bernstein ring of the fusion system, the p fusion system of G. And that's a proof. So in the case of the principal idempotent, we have these three different equivalent descriptions of what this ring really is. So how does it show up in Jesper's work? Let's summarize all of this in a big diagram. So theorem. Actually, this is a collection of several really deep theorems. Maybe I shouldn't just call it theorem. There is a commutative diagram as follows. Okay. In the first line, I want to look at the Grothendieck group, or Grothendieck ring, of essentially maps from G to sigma n. But I take homotopy classes of classifying spaces and look at the Grothendieck room where I assemble over all n. I'll get a map to the Bernstein ring of G, and this is an isomorphism. And if you look at it closely, it shouldn't be too hard to see that this is true. It's due to a classical result by Hurevich. So you should think about this as group homomorphisms from G to sigma n. So G acting on a finite set with n elements, and you take all the n, you get all the finite n sets, and you take the Grothendieck group. So this is just rewriting the definition of the Bernstein ring. And now what I want to do on the right-hand side is go to the Bernstein ring of the fusion system instead. And in the last step, go to the Bernstein ring of the fusion system and p-complete here. And for some technical reasons that I don't want to talk about, we have to take the p-completion in the category of augmented rings, z-augmented rings. But you can ignore that if you want to. And it turns out that due to work by Antonio just left, right? So work by Diaz, Liebman, I think, and also Kari Ragnarsson. There is a reformulation of the Siegel conjecture, or the P part of the Siegel conjecture if you want to. And it says that we have a bijection as follows. We take homotopy classes of maps from BG to basically the P part of the infinite loop space given by the sphere spectrum, which should be this object here. And then their version of the Siegel conjecture tells you that this is an isomorphism of rings, I guess. You mean the plus construction of Quillen? I p-completed, so in particular I did HZ localization. HFP localization is stronger. So it's automatically plus constructed or completed. And then it's a theorem by Jesper I guess it's his main result that he will present tomorrow, that you can fit something in here, which is in between the definition of the Böhme ring, or this classical reformulation, and the Siegel conjecture. And you can think of it as an uncompleted Siegel conjecture, because we didn't p-complete here. So what is this object? You take the Grothendieck group, you copy what's up here. The only thing you change is you p-complete b sigma n. And then the statement of Jasper's theorem is that you have a canonical ring isomorphism like that. And I hope we will give you all the details tomorrow. Okay, I think this is the first part of my talk. There any questions so far regarding this before we turn to stable homotopy theory? Oh yeah, I should mention this. This is a really good question. So Jasper's theorem neither implies nor is implied by the Siegel conjecture, as far as I know. But it uses a lot of deep theorems from homotopy theory. It uses equivariant Barrett-Quillen. I think there's the Sullivan conjecture hidden in there somewhere, vanishing of higher limits. It's a lot of deep theorems, but not the Siegel conjecture. Okay, let's move on to the stable realm. Don't forget the door code. So here's the stable dress splitting. Okay, so I understand that this is a fusion systems audience, so I shouldn't go too deep into stable homotopy theory. I'll try to give a very intuitive treatment without technical details. And I hope in the end I'll come back to fusion in G. But we have to fix some stable homotopy notation. Okay, I'd like to write SP upper G for some good category of G spectra. Good category of genuine G spectra. I don't want to attempt to define what good means in this case, and I don't want to try to explain what genuine means. Let's just believe there are objects like this, and they represent well-behaved G-equivariant cohomology theories. And I want to introduce a shorthand. So call a commutative ring G spectrum a G ring. Because I really don't want to say equivariant commutative ring G spectrum all the time. So I will just say G ring, but it always means commutative in particular. And I also want to assume that my category SPG satisfies the following. I want to assume that the category of G rings is just the same as commutative monoids in my category. And we know that we can do that, and today we don't care about the details. So in particular, I want to think about a G ring as something that has a multiplication like this, satisfying associativity and commutativity. Okay, what do these spectra look like? Here's an example. It's the one we will need today. The G-equivariant sphere spectrum. It's denoted by SG. It should be given by taking a G representation V and then sending it to its one-point compactification at the level V in the spectrum. So if you've seen classical spectra indexed on the natural numbers or integers, I want spectra indexed on G representations. Here's a fact that we will need. If you look at the homotopy groups of a spectrum, let's denote them by pi. So now I have to introduce a lot of decoration here, so I want pi v, and here an h. of some spectrum X. It doesn't have to be a ring at this case, at this stage. This should be, okay, I suspend by V, take the equivariant sphere spectrum, map to X, and take H homotopy classes of spectrum maps, equivariant spectrum maps. And what I want to say here is that this collection forms an ROG graded Mackey functor. So ROG is the real representation ring. So for my V here, I can plug in representations. And it also varies in H. And I have restriction maps and transfer maps. And then Jesper already mentioned this yesterday in his talk. We have a theorem due to Siegel, which is often called the equivariant top theorem. It identifies pi naught of the sphere spectrum as a Mackey functor. So I'll leave it blank here. So it's the whole Mackey functor pi naught of the sphere spectrum. Is as a Mackey functor the same as the Burnside ring Mackey functor. So now we see how the Burnside ring appears in stable homotopy theory, equivariantly. And since this is a talk about the dress splitting, and I'd like to look at the p-local dress splitting, is it still on the board? It's up there. We really don't want to look at this, but we want to make the p-local Burnside ring appear in stable homotopy theory. So we need some way of inverting elements. We need some kind of localization here. So this will be the next thing. Definition. So I guess we want to start with a G ring. For a G ring R, I want to write, I also need something to invert, sorry. We have alpha, say it's in pi star upper G of my ring. I want to write R alpha inverted for the following construction. I want to take the homotopy colimit over a sequence like this, where I take R, multiply by alpha, and do it again and again. Maybe it's not clear here what multiplication by alpha means, because alpha lives in the homotopy groups, and I want a spectrum map. So let's try to figure this out. R is equivalent as a G spectrum to R smash the sphere spectrum, which is the monoidal unit for the smash product. And then I can define a map from this to R smash R and use the multiplication here. And the lower horizontal map is just R smash my element alpha. And this is a well-defined multiplication by alpha. We don't have to worry about left or right multiplication because we assume we have a commutative ring spectrum. And this gives some sort of localization of spectra. And the following holds. Maybe it does. Maybe I have to fix, like maybe I have to say left multiplication now. Otherwise I have to introduce grading, that's right. I think I don't need it for my talk. So for my talk I can really assume it's in pi naught. Okay. So what does this localization satisfy? If we're looking at the homotopy groups of the localization on the spectrum level, this will be the same as taking homotopy groups first and then inverting the element alpha. So we recover classical localization of rings. And now we have all the pieces on the board for talking about the stable dress splitting. No, and I cannot because there are some subtleties involved that I will talk about later But yeah, don't spoiler. The stable dress splitting. Okay, so we have the dress splitting on the level of homotopy groups of the spectrum, and then we see that on the spectrum level, if we take the sphere spectrum, actually the p-local sphere spectrum, where you invert primes, then this is weakly equivalent to a wedge running over p-perfect subgroups, L of G, or conjugacy classes of those. And here you get localizations where you invert the idempotent EL. So this is the spectrum level version of what I call the dress splitting. I'd like to make one observation here, which is really interesting. No. Well, no. No. Actually, the remaining part of my talk will be about the multiplicative nature of the splitting, so I'll talk about it in detail. You're way too far ahead. You're too fast. Okay, one thing we should observe is, so we're talking about G spectra, but we all kind of know spectra. So what is true if we just restrict to non-equivariant spectra? If we look at the underlying non-equivariant spectra, and the following holds. So if we restrict from the group G to E, one of those summons p-local sphere spectrum and then EL inverted. The following is true. This will be, well, non-equivariantly for the trivial subgroup, equivalent to the classical sphere spectrum, the non-equivariant one, or contractible, depending on whether L is gives the principal idempotent or not. Oops. So it also says that non-equivariantly, the splitting is not really a splitting, it's trivial. You say x is x plus 0. And now the question that Irakli just mentioned, is the dress splitting multiplicative? And for that question to make sense, we have to first ask, are the pieces of the decomposition, are the spectra where we invert EL actually G rings? And there's something we can say about it. So this shows up in Jesper's work. So codate. The theorem says this is true for the trivial, or the principal idempotent. The theorem says this object is a G ring if L is the trivial subgroup. And the more general answer is all the other pieces will not be G rings. They will not be G rings. And in order to, so it's kind of silly because we have something that should behave like a ring. We localize, we invert elements, and it's not a ring anymore in the sense we want it to be. And to explain what's really going on there, we're moving on to part 3 of my talk, which I call equivariant commutativity. Maybe I should pause here for a second and ask for questions before we move on. Do you have any questions at this point? Oh, so we have, yeah, so we have idempotents indexed by subgroups. In particular, we have an idempotent EE. So the theorem says that SGP with EE inverted is a G ring. Yeah, it's the identity subgroup. So for each p-perfect subgroup L, we have an EL. In particular, we have one for the trivial subgroup or the identity subgroup. And there we can say the spectrum is a G-ring. And in the other cases, it will not be true for some reasons that I'm going to explain now. Unless you have more questions right now. I haven't really thought about it, but you're probably right. Okay. Maybe this is actually a good time to clean the blackboard. So what we're going to see now is some really subtle behavior of equivariant spectra. It's not true non-equivariantly, because non-equivariantly everything usually behaves in a nice way. So here's some intuitive approach to ring spectra. What's the multiplication? Multiplication on some ring-like object R, and I really want to be very vague here, should be something that has as input two elements in R. So it's defined on the tensor product or smash product, which we might also write like this, and maps to R. And this map should satisfy some axioms, like associativity, commutativity, so on. You can also think about it in a different way. You can think about it as a bunch of coherent maps which take as input n elements and then tell you what their product is, tell you how to multiply them, and also satisfy some axioms. And here's one way to think about what an equivariant, a genuinely equivariant multiplication is. You want coherent maps, so equivariantly. You want coherent maps. They're not just defined on n tuples of things in R, but here you want something that G can act on, and then have maps like this that satisfy a set of axioms, where this thing A, the index of our smash product, is a finite G set. So we're not equivariantly, we shouldn't only be acting on the objects and the maps, but also the things that give the products, that define the products, the indexing sets of the products. Let's get a bit more precise. Here's a construction due to, I guess, Hill-Hopkins and Ravenel, which is called the norm on spectra. So it should be a construction that has as input an H equivariant spectrum and gives us a G equivariant spectrum. And the idea is that if you have an H spectrum X, you send it to the smash product of X with itself, where as an indexing set you take G mod H. And then if you want to act by an element in G, you will have some like part of it in the cosets here that permutes the cosets, and some H part of it that will act on X. And you can use this to define a norm on homotopy groups. Or if you don't like the word norm, you can also call it multiplicative transfer or tensor induction or whatever. Let's write n from h up to g for this map. I only want to define it on pi naught because it's much simpler to write it down, but you can also define it for higher homotopy groups. But today we don't care. Here I guess I just want to, my ring. And then we want to map up to the G homotopy groups of R. So what does it do? An element in here should be represented by some map from the sphere to R, and then an H homotopy class. And then I can send it to the following. So it turns out that we can identify the spectrum with the norm of the sphere spectrum. And then here we can map to the norm of R, where we just use our map F several times. And here we just multiply. It turns out that this gives a well-defined G homotopy class, and this is the norm on homotopy groups. So what kind of properties does this norm have? It's a proposition. I think the first one to prove it was Brun. And he proved the following. He proved that if R is a G ring, then the functor pi naught blank of R is a so-called Tambara functor. I guess this is not a well-known definition, so let me explain what that means. We've already seen that it's a Mackey functor, and this is part of the data here. So this construction is a Mackey functor. So it has restriction maps, it has transfer maps, but it also has multiplicative transfer maps given by what I call the norm. Mackey functor plus norm maps n hk from the k homotopy groups to the value of this functor at h for all k inside h in G. Plus a list of axioms that ensure that the norm is compatible in the right way with restriction and transfer. It's always good to see an example. I will just copy an example that's already on the blackboard. If you take pi naught blank of the equivariant sphere spectrum, we've already seen that as a Mackey functor, it identifies with the Burnside ring Mackey functor. This is actually also true for the Tambara structure, for the norm maps. So this is true as Tambara functors. And this is only a statement that has content if I tell you what the multiplicative transfer on the Burnside ring is. So the norms here on the right-hand side, say on a finite G set A, are co-induction of G sets. Remember, co-induction is maps, H-equivariant maps from G to a finite G set A. Or if you prefer to think about index products, you can write it as a product over G mod H of copies of A. And then it's not extremely surprising that something defined in terms of equivariant smash products here translates to something defined in terms of equivariant products of G sets there. Good. So let's go back to our original question, which is right up there. Let's phrase it a little bit more general. So if R is any G ring, doesn't have to be the sphere spectrum, but it's what I'm interested in. And if we have some homotopy element like this in R, the question is, is the localization a G-ring? And I guess we already mentioned several times during the talk that this is not actually true, or not always true. So what is it that we can say here? If we're in the non-equivariant case and we look at the trivial group, it's always true. There are no issues, no subtleties, it's fine. So here the answer is yes. If the group is non-trivial, the answer is no in general. And what's actually happening here is, in general, localization might destroy some of the norm maps. Some of the maps which multiply equivariantly for certain G sets here. Maybe I should write A here for some A. You will always have the ones where A is a trivial set, so we just multiply n things without acting on the things you plug in. But if there is a non-trivial action on A, you might destroy some of those maps by localization. By which I mean that the localized ring does not admit such maps anymore. Or equivalently, you could say that might destroy some of the norm maps in homotopy groups. So it's good to think about G rings as something that's a ring spectrum in the non-equivariant sense plus norm maps, either on the level of these equivariant multiplications, or if you prefer to think algebraically on the level of homotopy groups as multiplicative transfer. So this is the extra structure that we have in the equivariant case for ring spectra. Yeah. And if I have time at the end, and I think I will have, then I'll write down a detailed example. So we will see that behavior for a nice group. It is possible to produce extreme examples. I think the first one was given by Mike Hill. I will not spell out the details because I want to spell out the details later for the dress splitting. But you can produce a map alpha, and it's not really hard to write it down, such that the localized sphere spectrum, call it R. What do I want to say? Only admits maps that multiply equivariantly if A is a trivial G set. So in general, you might destroy some of those maps, and you can produce examples where you destroy all of them, but the ones that you will always have, that you will definitely have, that you cannot destroy. Sorry? I'm cheating here. It's living in degree minus reduced, what is this called? Regular representation. Yeah. I'm cheating here. This is not actually in degree 0. I don't want to talk about grading issues today. Yes, any finite group. Because this construction only uses one thing, it uses the existence of a regular representation of G. So if you want, I can write down alpha. So you can include 0 in the regular representation of G minus the trivial representation, which gives you a map on the one-point compactifications, and then you desuspend by this thing. Let's call it row twiddle, and then, yeah, sorry. So this is actually a map from the sphere spectrum desuspended to the sphere spectrum. And then to see what happens in this example, you have to think about what restrictions of the map alpha to subgroups are. Then you see that for all proper subgroups, this map is null homotopic. That's the idea. Okay. Let me give yet another perspective on localization of ring spectra, or localization in general. So here's another point of view that I really like, and it's due to Mike Hill and Mike Hopkins. So let R be a commutative ring. Here I really mean commutative ring as in your undergraduate. And say we have some element alpha that we want to invert. Then let's look at the following two constructions. Let's write L alpha mod for the following construction. The module localization, where you take the colimit along a chain of module maps given by multiplication by alpha. Then you take the colimit in the category of R modules. You've all seen this construction before. And let's write L alpha alg for the algebra localization, where you look at the following pushout. You take a polynomial ring over R, considered as an R algebra. You have a map to R by sending x to 1. And you have a map to polynomial ring where you send x to alpha times y. And then it shouldn't be too hard to see that if you take the push out in the category of R algebras, all you did is inverting alpha. Because, sorry, this is a y. And multiplication by alpha becomes a unit, or becomes invertible. And then both of these constructions satisfy universal properties. This is an algebra. You can just look at it as a module, and you get a map from the module localization, which is universal in some sense, to the algebra localization, which is also a module with the same properties. And what you learned in your first course in commutative algebra is that this map is an isomorphism, and both constructions realize what is called the localization of a ring. So, how do I want to say this? Let's call this map lambda. And it's clear that in this setting, lambda is a canonical isomorphism. So what is true for spectra? So if you carry out the same constructions for non-equivariant spectra, and in my terminology this would be called an E-ring, or non-equivariant ring spectrum, commutative. And you also have to replace the colimit by a homotopy colimit, and this will be a homotopy pushout. Then lambda will be a weak equivalence. And then you see that inverting alpha actually has the right homotopy type of how you'd like to think about localization. But more generally, for G rings, this is not true anymore. The two different ways that you know of how to produce localization do not agree for equivariant ring spectra. Hill and Hopkins managed to explain this situation a little bit more. It's the following theorem, which tells you that lambda is a G weak equivalence if and only if the following conditions are satisfied. We want that the norm of the restriction of alpha divides the thing that you get if you only restrict to the right group. So this condition says that if you, for all k in H and G, so this condition says, okay, we have the homotopy groups at level G, level H, level K. We have alpha living here, and we can restrict down here, and then norm up. And what we get should divide the thing that we get if we only restrict here. For all K, H, and G where this makes sense. Okay. Now we're deep down in the theory of equivariant commutative ring spectra. What is this talk actually about? What do we actually want to do? Let's recall how we started, how we got there. So it turns out that these conditions are not satisfied for all but the principal pieces of the dress splitting. So they won't be G-rings in a strong sense, but they will be kind of incomplete G-rings where you only have some of the norm maps. And then the next goal should be to understand the, let's call them incomplete G-rings. That we got from the dress splitting. Remember, we started with a p-local sphere spectrum equivariantly, and then we inverted certain idempotents EL. And we're still trying to understand the multiplication on those things. And they will be some sort of incomplete G-rings that are ring spectra non-equivariantly, but have only some of the Hill-Hopkins-Rabanel norm maps. So only some of the very rich extra structure that you have equivariantly. And now this theorem of Hill-Hopkins tells you that this is actually equivalent to understanding co-induction of G-sets. Because all we have to look at is multiplicative transfer on the level of homotopy groups in the p-local Burnside ring and its localizations. I guess this is what you asked earlier, right? And now it would be the perfect time to write down an amazing theorem that explains the entire structure of these things, but I don't have one. What I can write, sorry? Yes, they are ring spectra, but they are contractible. Yeah. It's kind of a silly statement. But also more generally, if you don't take the sphere spectrum but any G ring, you might get something non-trivial which also has part of the extra structure. In this case, it's trivial, yeah. So the best thing I can offer today is a conjecture. And I think I'm close to proving it, but I need some more time. So if P is a prime that does not divide the order of G, then I hope the following is true, and I hope I'll prove it soon. The spectra we're looking at, the spectrum will admit a norm map N from K to H, if and only if one of the following holds. Either satisfies that L is not subconjugate to H and G. Remember, L is the subgroup that gives the idempotent. Or L is actually is a subgroup of all the G conjugates of K. Now I guess we're getting back to fusion system land, because here we only have to look at conjugation in G to understand what's going on. So all of this theory of ring spectra in this case reduces to G conjugation. Right, then it's the same as the rational splitting, yeah. And then the next step will be to try to understand how you get back to something that actually divides the order of G. So how much more time do I have? 3 minutes? So I said I'd like to give one example for a certain group. So I'd like to show you what it looks like for the symmetric group on 3 letters, and sigma 3. Okay. So dress splitting for sigma 3. So first we need to know what the p-perfect subgroups are. So how did I write this? The 2 perfect subgroups are the trivial one and A3. The 3 perfect subgroups will be trivial one, C2, and the entire group. And then if you have something which is not 2 or 3, it will be all the subgroups. They will all be p-perfect or q-perfect. And then I'd like to arrange this in the diagram as follows. So here's the case for p equals 2. Let's say we have the subgroup H down here in this column. Let's actually arrange it as it looks like in the subgroup letters. And then here I want to write down the rank of the Bernstein ring of H, localized at P, and then with EL inverted. Here we have only 2 cases. We have case where L is E and where L is A3. So I hope that doesn't look too complicated. And then the splitting looks as follows. This thing will have rank 4, it's the Bernstein ring of sigma 3. So rank 4 is a ZP module. Here we only get half of the structure for each of the idempotents. And then the ranks here are 2, 1. And here you have the norm maps in between them, because we know that in the case of the principal idempotents, we will have all the norm maps. And here we have rank 1, and those 2 modules down here will actually be trivial. They are killed by the idempotent. And then there's a trivial norm map here. And my conjecture says that we cannot have norm maps here. And in this example, I computed it by hand, and it's actually true. So since I'm running out of time, let's skip the prime 3, and let's look at p not equal to 2 and 3. Because this is what my conjecture actually is about. So if we look at the ranks here we actually have 4 idempotents. We have the trivial one. Sorry. We have C2, A3, and sigma 3. And then if you compute the ranks, you will have 1, 1, 1, 1, 1, 1, 0, 0. Sorry. And here you will only have something at the entire group. All the others will vanish. So for trivial reasons, we will have a norm map here, 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 between the 0 modules. This is not really an interesting statement. By Jesper's theorem, we know that this is a G-ring, so we will have all the norm maps showing up. And then the only question is, so the norm map should be multiplicative, so we cannot map from 0 to 1. So we won't have norm maps here, for example, or there. And the only question is, do we have norm maps here? There could be one. Do we have norm maps here? And then you have to study conjugation in the group. And since A3 is normal, you will see that we actually have a norm map here. And since conjugates of C2 don't satisfy the condition that I stated in the conjecture, you don't have a norm map here. I hope this picture makes sense. Maybe this was a bit fast. Yeah, otherwise I wouldn't write down the example. I wouldn't write down the conjecture if I knew a counterexample. I know that in this example the conjecture is true, yeah. Okay, I should stop here. Thank you. Right, yeah. I hope I managed to explain that we can reduce the problem of understanding the ring spectra to just computations in a Burnside ring. So what I did here, you mean? Oh, okay. So in the Burnside ring, it's just multiplicative induction or co-induction. So in the Burnside ring, you have a norm map. Let's just look at the Burnside ring. Let's not localize anything. So we have a map that goes up from a smaller group K to a bigger group H. And it's defined on G sets by sending a G set, on K sets, by sending a K set A to what people often call the co-induction. We take H equivariant maps from G to A. This is a right adjoint to the restriction functor. Oh yeah, sorry. Of course I want to use K here in H. So this is what people call co-induction of A. And you have a K sets, H sets. You have a restriction functor. You have a left adjoint, which is induction. And you have a right adjoint, which is co-induction. And it's this functor. And here I try to indicate which of those norm maps, NKH, survive after you invert elements. And here all will still be well defined on the localization, but here those two are not well defined anymore. They're not compatible with localization. Which means that on the spectrum associated to this picture, you will not have all the structure of a G-ring, but these two parts of the structure are missing. Right, yeah. It will not form a Tambara functor because it's the same as a transfer, so it's additive but not multiplicative. The representation ring actually is a Tambara functor, but the multiplicative transfer or norm is not given by co-induction, it's given by tensor induction. So it's kind of an accident that here co-induction and norm are the same. Yes, that's better, yeah.